Welcome to the video on properties of Z transform. So we discussed about Z transform, and the first property of Z transform is linearity. It's a linear transformation. You have an xn, which is a, let's say, linear combination of x1 and x2n. Then the Z transform will be also linear combination of x1z and x2z. Right? And the ROC, very important, because we saw that ROC is very important in defining that which signal corresponds to which Z transform. So ROC for this xz, it contains R of x1 and R of x2. Basically, xz will converge for all those points where, all those z where both x1 and x2 converge. But there can be some other z regions, other points where the xz converges because of pole zero cancellation, right? A simple example could be something in x1n might be cancelled by something in x2n, and this means that the constraints are reduced. So that is why we are saying R of x1 intersection of R of x2 is at least the ROC for xz, but there can be other regions as well. Okay, so the proof of linearity, we know by definition xz will be alpha, basically the Z transform of this linear combination. Now we can open up the brackets and take the summation inside, and we see, yes, indeed it is a linear combination. That's it. So, and the first series will converge when the mod Z is in R1, and the second series will converge when mod Z is in R2. And for the values of Z where both converge, basically you take the intersection, right? So this is minimal, and you know there can be pole zero cancellations, because of which there can be some other regions where xz will still converge, right? But at least this is the region where it must converge. It will converge. Okay, let us see an example in this regard. As you know, x of z, when x of z is 1 upon 1 minus a z inverse, this is a standard form, and the pole appears at a when z is equal to a, and if mod z is outside of mod a, basically it lies in this orange region, then you know that the inverse Z transform will be an un, the right-sided exponential. But if I choose this as my ROC, the inside green region, then I know the ROC is mod z less than mod a, okay, means the inside of this circle of mod a radius, and then the x of n, the inverse Z transform, will be xn is minus anu minus n minus 1, the left-sided exponential, right? So basically the same x of z, depending on the two regions of convergence, it can correspond to either right-sided exponential or a left-sided exponential. Now with this recap, basically this is a recap for what you learned in your previous slides, in the previous videos. Let us consider this example. Given xz is 1 upon 1 minus a1z inverse plus 1 upon 1 minus a2z inverse, how many xn can it correspond to, right? Xz is given, what xn will lead to this xz? And you know, we can get it from the ROC plots. Basically, if you choose one particular ROC, then the xn will be different. Let us see all of these cases one by one. Okay, consider the first case where you have the outside region. Basically, z is greater than mod a1 and also greater than mod a2, which means the z lies in this. So this is my region number 1. It's the orange shaded region. And so if my ROC is this, basically if I know that my Z transform converges for all such C, what will be xn? when our x of z is what I gave in the previous slide. So this means that both are right-sided sequences because z is greater than mod a1, greater than mod a2. Both are right-sided sequences, exponentials. So a1 power n un, a2 power n un. So which means my x of n is simply a1 power n un plus a2 power n un, right? So for the ROC1, this is my x of n. Now consider the second case when my ROC is between these two concentric circles. Basically, it is a ring. Reason number 2, this is a ring, which means my z is greater than a1, mod a1, and z is less than mod a2. If this is my region of convergence, then I know it is one right-sided and another left-sided sequence. So since it is outside a1, so a1 to the power n un is the inverse z transform, and since it is inside a2, it is minus a2 power n u minus n minus 1. So basically, these two ROCs, the intersection is given by this ring, right? The intersection. Okay. And so combining these x1 and x2, I get my xn as this thing, just the sum of x1 and x2, right? Now consider the third region now. This is the third ROC region. If my ROC is this, basically if I am given that my xz is the form which I showed in the previous slide, and my ROC is this, then what will be the inverse z transform, or what will be the xn which corresponds to that xz and the ROC? So now you notice that both is inside a circle. This one is inside a circle of radius a1 mod. This is inside the circle of mod a2. This means both are left-sided sequences, left-handed sequences. So x1n is a left-handed sequence, left-sided sequence. x2n is a left-sided sequence. So my x of n is simply the summation of the two. Okay. Now consider the fourth example, which is z is less than a1 but greater than a2. Is it possible? No. The intersection of these two sets will be null. Means the intersection does not exist. There is no overlap in the ROCs. So this means our xn does not exist, right? I cannot have, so because, okay, if I just translate x1 is less than a1, so it is a left-handed sequence, and z is greater than a2, so it is a right-handed sequence. But there is no z for which x1 plus x2 converges. Basically, the z transform does not converge for any z for this sequence, right? So here given that a1 is less than a2, right? So S is clear from the mod a1 is less than mod a2, right? So such inverse transform is not possible. So basically only 3 inverse transforms are possible, but this case is not possible. Okay, now let's look at some other properties of Z transforms. One such property is time shift. Basically you have, there is a time shift in the X domain. Then how will the Z transform change? The Z transform will be simply Z to the power minus n naught times xc. Compare this with the normal DTFT and you will see that yes, it is what? The same result what you observed in DTFT. E to the power j minus, e to the power minus j omega n naught, right? And what is the ROC? The ROC will be same as ROC of x, except for possible additions or deletions of z equal to 0 or z equal to infinity. Because if xz does not have any pole at 0, and I am adding n naught here, so this is adding a pole at 0, right? And similarly, they can be, if my n naught is negative, then I am adding a 0 at z equal to 0, right? Okay, so now what is the proof? So let us find out the proof. You have done such proofs in DTFT, so it should be very easy for Z transforms as well. So you know your, let's call this as y of z, the whole thing, which is a Z transform of x n minus n naught. So by definition, it is this, right? The signal times z to the power minus n summed over all n. Now, let n minus n naught equal to m, substitute it, and you get x. So you have gotten xm is z to the power minus m plus n naught. You take out z to the power minus n naught outside because you want to sum only over m, and you get x of z. So this is what you wanted to prove. So hence proved. Now what about the ROC? So this series will converge for mod z belonging to the region of convergence of x, right? So which is either a ring or regions inside or outside the circle. So the same convergence zone. So basically the ROC is the same. Now, how does the Z transform change if we multiply x of n with an exponential sequence? So z0 could be anything; it could be real or complex or whatever, but to the power n is important. So how will the Z transform change? So let us see. So y of z is simply the signal into z to the power minus n summed over all n, and so basically here z naught to the power n can be written as z naught or 1 upon z naught power minus n, and you can club the two together. So z upon z naught power minus n, and you know this is the x of basically z upon z naught. So this is capital X z by z naught, right? Simply you have scaled your z by a factor, a constant z naught, right? So I can write here my z naught belongs to complex numbers and it's a constant with respect to n and z. Okay. So, and what is the region of convergence? So for this to converge, this scaled z should lie in the ROC of x. So z by z naught mod should be why mod, because you know every time you are only concerned with the radius, because the ROC is always a circular region, either a ring or inside a circle or outside a circle. So we are interested only in the mod, and you know the proofs, we have already seen that before. So mod z upon z naught belongs to region of convergence of x, and that is what the ROC is, mod z naught times Rx. Okay. Next is differentiation of xz. If I differentiate my xz, then how will the inverse Fourier transform look like? Or sorry, inverse Z transform look like? So the result is that n of xn will correspond to minus z dx upon dz, and the ROC will remain same. Let us prove this now. So the proof is given here. You start with the basic definition of x of z. X of z is simply x of n z to the power minus n summed over all n, and you differentiate it. That's what you are interested in. Differentiate both the sides with respect to z, and what you get is, okay, xn is constant with respect to z, only this minus n z power minus n minus 1, right? And just a little bit of rearrangement, and you keep nxn z to the power minus n, all terms which depend on n inside, and other things you take out. And you know what is this? This is Z transform of nxn. So this is the Z transform of nxn, and this minus z inverse I take to the other side, and it becomes minus z dx upon dz, right? So this is what we had to prove, that the Z transform of this thing is this thing. Okay, and the region of convergence. When will this converge? This will converge when this sum will converge, basically if mod of z to the power minus n lies in the our region of convergence, because this n plays no role. So convergence is determined by mod z belonging to Rx. That's it. Now conjugation. If I take a conjugate of x of n, then how does my corresponding z transform change? So that is given by x star z star, but the ROC remains same. So proof. Let's see the proof. So y of z, basically the z transform of this thing, is given by this simply by definition. Now you have to rearrange so that you can arrive at a form of x of z. So basically you get free from this star, take it outside, and that will correspondingly put a star on z. So this is basically x of z star, right? So this is x of z star, and on top there is a star existing, so which appears here. So, and where does it converge? It converges whenever basically z star belongs to Rx, but since z star and z have same modulus, so I can say mod of z belongs to Rx, right? So it does not change the region of convergence. Okay, now time reversal. If I reverse the time, if I take x of minus n, how will the z transform change? Okay, let's see in the proof. So the z transform of yz is given by simply by definition. Now I have to make it xn somehow so that I can get a form of x of z. So just replace minus n with m and rewrite, substitute the value, and this is what you get: x of m, z of m, z to the power m. So you know how to handle these. This is basically 1 upon z to the power minus m. I'm sorry, minus is there. 1 upon z to the power minus m, and this means this is simply the z transform x1 upon z, right? And for this to converge, I know 1 upon z now should lie in the region of convergence, which means z lies in 1 upon Rx. That is the proof. Next, convolution. How, if I convolve two signals, how does their z transform change? For that, you have to recall that convolution in one domain causes multiplication in the other domain, and the same result is true for z transforms as well, and we will be proving it here. And okay, how will the ROC change? ROC is basically the intersection of x1 and x2 ROCs, but it could be larger because of pole zero cancellation. Okay, let's see the proof of this convolution property. So you write down, by definition, it is this, the signal x of n is given by x1 convolved with x2 fn, and e to the power minus n. By definition, it is like this. Little bit of rearrangement now. Take the k out and n inside. And what is this now? This is simply z transform of x2 n minus k. And you have already seen what is the effect of time delay. Time delay brings an z to the power minus k term. This time delay causes z to the power minus k, and everything else is same, x2 of z. Okay, now consider the next step, where basically you take the, okay, this is just, we have already seen. Now you take x2z outside because it's not a function of k, and the remaining terms, and you know this is simply x1 of z, right? This is simply by definition x1 of z. Now let's see the region of convergence. So when does it converge? It converges whenever this converges, basically when this mod z belongs to R2. Okay, there is a slight change here. This one should be R2 and this one is R1, right? So it converges when z belongs to this as well as this. So basically it's the intersection of the two regions. But you know, since this is product, it is possible that it has a pole at 0 and this one has a 0 at 0, and both of them get cancelled and we get nothing at 0. So there may be pole zero cancellation to allow convergence for some other regions as well. That's it. So that's the convolution. So these are some of the properties which are also discussed very nicely in this reference called Oppenheim chapter 3, section number 4, called Z transform properties. Thank you very much.